Welcome to 6.4. This is looking at irrational numbers. We already have looked at the square root of 2. We proved that that was irrational. We're not going to prove that these other ones are, but they are indeed. Some of them are kind of famous. Let's just look at a few of them that you might know about. First one is pi. First of all, what's the definition of pi? You might know the value of it. It's 3.14, and that's as far as I know. Since it's irrational, it goes on forever. It won't stop and it won't repeat. It just keeps on going. And I think it's been taken to billions of places at this point, maybe even more. And so that's the value of it. What's the definition of it? The definition is if you take a circle. Does that look like a circle? And you first find the distance around it. The circumference is the outside, the distance around, and then the diameter is the distance across. Then the ratio of the distance around it divided by the distance across is the value of pi. So when I show pi to my math classes at Davenport, I go out into the parking lot or one of the athletic fields and I take various lengths of rope and I have one student stand in the middle and the other one pace the number of paces it takes to go around the outside, and then they pace across, the other person holding the rope, and if they do a good job at it, they end up with something just a little bit over 3.14 if they're really getting close. And doesn't matter what the size of the rope or the cord or the thread or anything else is, that ratio is always the same. So that's the definition. And since the diameter, remember what the radius of a circle is? The radius is r. The diameter is twice the distance of the radius. So from this we have that the circumference over twice the radius is equal to pi. And then, if you multiply both sides by 2r, you get that the length of the circumference is 2 pi times r. Doesn't matter what order you put them in, usually you write the constants first. So there's the relationship between the radius of a circle and the circumference of a circle. So that's the circumference. Now, what happens if you want the area of a circle? Well, I saw a really clever proof of this. There are lots of more rigorous proofs. This one takes a little bit of imagination, but it does a nice job. You take a circle of radius r and you just cut it up into a whole bunch of very small wedges. And then you take those wedges and you just take them out and you just kind of lay them flat on each other. Each of them are going to have a little bit of a circular edge to them, but they're going to be pretty close to being straight. And once you lay all those on top of each other, then you get yourself basically something that looks pretty close to a rectangle. And the area of that rectangle is going to be the area of the circle because you've used all these wedges and just piled them up on top of each other to make this rectangle. So what's the area of this rectangle? Well, the area, the length of the base, that's just the length of one of these chords here, so that's going to be r. And the length of the side, well, the length of the side is going to be half the circumference, agreed? Because you're basically taking these things and putting half of them on this, half of them are on this side and half of the edges are on this side. And so since the entire circumference is 2 pi r, half of that is just going to be pi r. So half of a circumference, that's the length, is going to be pi r, and there you have r. So when you multiply those two together to get the area of a rectangle, you get that the area is equal to pi times r, or pi r squared. So there's kind of a cool way to see the area of a circle. So pi comes up almost everywhere. Whenever you have circles, you very seldom don't have a pi. I can think of one place where you don't. Turns out, just as a quick aside, if you take a circle of radius r and and you think of that as a bicycle tire, and that bicycle tire runs over a lightning bug, and the lightning bug gets caught in the tire, and then you watch that lightning bug at night when all you see is the light of the lightning bug. It's going to make a big arch like this. It's not going to be a circle because that circle is moving, and it turns out that this length is 8 times r, which is kind of cool. It's exactly 8 times the length of the radius. So anyway, that's one thing where it doesn't use pi. But anyway, pi not only comes up with circles, it comes up other places too. Here's just a couple places where it comes up. It's really kind of interesting. If you take all the numbers, 1 minus 1/3 plus 1/5, all these odd numbers I should say, minus 1/7 plus 1/9 minus 1/11 plus 1/13. You see the pattern? You've taken odd numbers and you're alternating plus or minus. When you do all that and add those all together, you go all the way out to infinity, never stop, and you multiply that by 4. You can show using some Calc 2, any of you that are going to go on to calculus, we show it here at Davenport. If you multiply that by 4, that converges to pi. So there's the way that you can get pi as good of an approximation as you want. If you only relied on making big circles and measuring it carefully, you'd never be able to get very far because the measurements themselves would be inaccurate. But using these mathematical techniques, you can get as close as you want to the actual value. And there's other ways to get pi as well with numbers which get much faster than this. This you'd have to go out a long ways to get very close at all, but there are other methods that are closer. I'll only mention one other way. This is really kind of neat. It's called the Buffon needle problem. If you want to, ask your teacher whether you can do this in class. I might do this in my Math120 classes if we have time. It's kind of cool. What you do is you give everyone in class a piece of paper that have lines on it which are 1 inch apart, okay? And then you give everyone also a needle. I just take little pieces of a paper clip, which are exactly 1 inch, and they have to take that needle and they have to just toss it onto this paper. So when it tosses onto the paper, it's just going to kind of randomly fall like that. It might fall like that, it might fall like this, might fall like this, might fall like this, okay? Sometimes it will cross the line and sometimes it won't. And it turns out, I won't go into all the math because, well, I'll just very quickly go through some of the math. Turns out all the different ways that needle can land, you can think of as being represented in a rectangle, which is pi units long and 1 unit high. Okay, I won't go into the details. And it turns out that all the ways that it lands so that it crosses one of those lines is represented by the area underneath this curve. This is the curve y is equal to the sine of x, okay? You need to know some trig in order to fully appreciate this. But it turns out that the area of this rectangle, well, you know that's the area is pi times 1, so the area of that is pi. And the area underneath this curve is 2, okay? And it turns out that the number of times that the needle crosses a line divided by the total number of times that you throw the needle, toss the needle, is the same ratio as 2 divided by pi. Okay? So if you want to know how many times, or if you want to evaluate pi, you can multiply both sides by pi, which will bring that up there. You can also multiply both sides by t, and you can divide both sides by c. So it turns out if you have everyone in the class toss it like 50 times, so each one is tossing it 50. 50 times 2 is 100, and you multiply that by the total number of people in the class, you'll get the total number of tosses. And then you have everyone count up how many times it's crossed the line, and you keep track of those, and you add all those up, and you take this and divide it by this, you're going to get something really close to pi. I shouldn't say really close. It depends on luck. It's a probability thing, just like throwing a die. But sometimes we actually get quite close. If you want to try this yourself, you can. Just make your own little paper and pencil, or paper and a little pin. Anyway, it's kind of cool because it's really neat because various people, when they give how many times it crossed, some of them will be 14 and some will be 19 and some will be 11. They vary all over the place, but by the time you're done and you add them all up, that gives you something pretty close to pi. So it's like a little roulette problem. So anyway, all kind of cool stuff. Okay? So that's all pi. Here's another irrational number, which is just as interesting. In some ways, you might call this the most beautiful number in the world. The author gives it the letter phi, and I think other authors have used that as well. It's not quite as well known as pi. 1 plus the square root of 5 over 2. Remember what the square root of 5 is? It's the number that when you multiply it by itself, you get 5. You add 1 to it, and you divide by 2. And you get something pretty close to 1.6. Do I have it written down? I don't. I think it's 1.61 or 1.67. I should have it written down. 1.618, something like that. Doggone it, I don't have it written down. Sorry about that. You can calculate it yourself. But anyway, here's where this number comes up. If you take a rectangle and you make the rectangle just the right size so that, I gotta make it just a little bit more square like that. Just the right size, I should say just the right shape, so that if you cut off a square, there you cut off a square, and let's let this distance be A, and we'll let this distance be B, and so this will be what? A minus B, agreed? A minus B. So this is A, this is B, and this is A minus B. Then, this thing has just the right shape so that the ratio of A to B, is exactly the same ratio as B is to this thing that's left over, A minus B. Okay? And so the question is, what particular ratio has that property? What does this what does the ratio of A to B have to be to have that property? The easiest way to do this problem is just to let B be equal to 1, and then for the ratio, all we have to do is to find the value of A, because A over 1 will be the ratio. So let's go ahead and do that. Let's just let B be equal to 1. And if we do that, we get what? A is equal to 1 over A minus 1. Agreed? And if you have that and you want to solve it for 1, then you first multiply through by the denominator here. And then you're going to get A times A is A squared. A times minus 1 is minus A. And then if you subtract 1 from both sides, you get that. So how do you solve this? Well, the way you do it is called the quadratic formula. And we'll learn about that later on. But it basically says you look at these constants right there, the 1, the negative 1, and the 1. And what you do is, by using those, you can solve for A. A ends up being equal to the negative of this one. Negative of negative 1 is going to be positive 1. Plus the square root of this number squared. Negative 1 squared is 1. Minus 4 times this number times this number. All divided by 2 times this number. And that ends up being 1 plus the square root of 5 divided by 2. So when you solve for that, that's where you get this number right here. So that's it's called the golden rectangle because it's a beautiful rectangle. This is also called the golden ratio because it's something very, very aesthetically pleasing. If you go to the internet and go to Google and put in golden ratio or golden rectangle, you'll find all sorts of things both in architecture and in art where they end up using this. Okay, another place where this shows up is in what's called the Fibonacci sequence. Okay? The Fibonacci sequence is what you get by starting with 1 and then another 1, and then you add those two together and you get 2. You add those two together and you get 3. You always add the last two together, so you're going to get 5. 3 and 5 is 8. 5 and 8 is 13. 8 and 13 is 21. 13 and 21 is 34, and they go on forever. It's called the Fibonacci sequence. These are also cool numbers, which are very much involved in not only art, but in nature. If you go to Google and say Fibonacci sequence in nature, or Fibonacci numbers in nature, you'll find all sorts of things, petals of flowers, and pine cones, and pineapples, and sunflowers, and so on, where these numbers show up more often than you would think. And it turns out that if you take any of these numbers and divide it by the previous one, as you go out farther and farther and farther, like 21, well, it's like 13 over 8, or 21 over 13, or 34 over 21. As you go out farther and farther and farther, those ratios approach this number again. Kind of interesting. Who would think that these crazy numbers here would have anything to do with a rectangle like this? But they do. And you can prove it. Here's the way you prove it. What you do is you say if this number is a sub n, that's your nth number in the sequence. This one here would be a sub n minus 1. And then this one here would be a sub n plus 1. And so there's 3 consecutive terms of the sequence. And so what we know is true in order to form the Fibonacci sequence is if you add those two together, you get the next one, right? You add these two together and you get the next one. So there's the relationship that defines the Fibonacci sequence right there. And then if you divide everything through by a sub n, look at what you get. You're going to get a sub n minus 1 divided by a sub n plus 1 is equal to a sub n plus 1 divided by a sub n. And now, what did we say? We said as you go out farther and farther and farther, this ratio here approaches some number. It's going to be some ratio. Let's just call it r, this thing approaches. So this is going to be r right here. Here you have 1, and I can do something kind of clever. I can write this as 1 over a sub n divided by a sub n minus 1. If I flip that over the line right here, then you take the reciprocal of it, and you're going to get this, and that just gives you the r again. Here's the same ratio that we have right here. So it's going to be 1 over r plus 1 is equal to r. And now if you multiply everything through by r, you're going to get 1 plus r is equal to r squared. And if you bring everything over to one side, you're going to get r squared minus r minus 1 is equal to 0. And notice that's the exact same formula we have up there. I'm going through this rather quickly. If you want to, you can slow it down and do it again, or you can have your teacher explain it to you again. I want to get a lot of material in kind of a short period of time here. But anyway, there it is right there. So it turns out that this golden ratio shows up both with the Fibonacci sequence and also with the golden rectangle. So kind of cool. So that's, as I say, it's considered by some people the most beautiful number. Okay. The last number I'm going to mention to you is the number e. It's another irrational number. It's It's another mysterious one. The value of it is, it's another irrational number. The value of it is roughly 2.7181. It goes on from there. On my bumper sticker of, not my bumper sticker, on the license plate of my car, I wanted them to have it be EXP271, and they wouldn't give that to me because it's too much like regular license plates. So I changed it to EXPLOG, which are two mathematical things that are inverses of each other. We'll learn about that later on too. All sorts of stuff you're going to be learning this semester. By the way, the reason I use EXP for exponential is because this is the basis for an exponential equation, which we'll be learning about later on. Anyway, where does this show up? One place where it shows up is that if you have the graph of y equals 1 over x, and there's 1 right there, and you look at the area underneath this graph and you ask, how far out do I have to go before the area underneath that graph is 1? It turns out you have to go out exactly as far until you get to E. Seems like a strange and unimportant little fact, but that turns out to be quite important, okay, in mathematics. Anyway, that's one place where it shows up. Here's another place. When I first got a calculator, I was kind of playing with it, and I remember I started experimenting with this sequence of numbers. I wondered what would happen as I go out farther and farther and farther, taking bigger and bigger values of this number right here, 1 plus 1/10 to the 10th power, 1 plus 1/100th to the 100th power. And this is really interesting because two things are going on at the same time. If you take 1 to any power, doesn't matter how big it is, you just stay with 1. Agreed? 1 to any power, no matter how big it is equal to 1. On the other hand, if you take 1 to any number which is just a tad bigger than 1, and you keep taking it to higher and higher powers, that's going to eventually just get as big as you want it to get. That's going to go off to infinity if you take some number here and just keep taking it to higher and higher powers. So here you're doing two things at the same time. The inner part here, inside the parentheses, excuse me, it's getting closer and closer to 1. It's really trying to hug the 1, and it knows that as it gets closer and closer to 1, it's going to, even if you take a very small, a number just slightly bigger than 1 and take it to the 10th power or 100th power, it's still going to be pretty close to 1, okay? So the closer this is to 1, you take it to big powers, it's going to stay close to 1. So this thing in here is trying to pull the number down close to 1. On the other hand, you take anything bigger than 1 and take it to higher and higher powers, this thing out here is trying to make it get bigger and bigger. So they're fighting against each other. This thing in here, as n gets bigger, if you go 1 plus 1 over n to the nth power, this thing right here is trying to suck it down to 1. This n out here is trying to make it go to infinity. So what does it do? Does it go off to infinity? Does it go to 1? Or does it go to something in between? It turns out it goes to something in between. It goes to the number e. Try it yourself. Just take 1 plus 1/1000th to the 1000th power, and you'll get something pretty much identical to that. Really kind of clever. So that's one other place where it shows up. Yet one other place where it shows up is, remember what factorial is? Do you know what factorial is? 5 factorial means 5 times 4 times 3 times 2 times 1. 2 factorial is just 2 times 1. 1 factorial is just 1. 0 factorial, you'd think that would be, it doesn't even make sense because you're starting with 1. But it turns out 0 factorial, it's convenient to define that to be 1 as well. And given that, it turns out that e is equal to what you get by taking 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial. You keep going all the way out, never stopping, and that goes to e. So here you have all these various things in mathematics that all go to e. You can see why it's a rather important number. So now you have it. What are all these interesting numbers we have? We've got 0 and 1, which are really important. When you're multiplying things by 1, it stays the same. If you add 0 to something, it stays the same. So these are called the additive inverse and the multiplicative inverse. Then you have this number e, and you have pi. And we're staying with real numbers, but if ever you want to deal with imaginary numbers, if you want the square root of -1, what is it? What's the number that when you take it times itself, you get -1? It turns out that's this number called I, which is yet another really interesting number. Okay, and so those are quite possibly the 5 most interesting numbers, important numbers in mathematics. And it turns out that there's one equation which relates them all together. There it is right there. E to the I times pi plus 1 is equal to 0. This is called Euler's equation. That's the way you spell Euler's. And not only does it have the 5 important constants, but it also has all the important operations. You've got your plus minus right there. You've got multiplication right there. And then you've got exponentiation, which is sometimes written like that. So it really combines everything. If you ever want to make a nice math t-shirt, that's the one to have. Okay, very good. Finally, since we're talking about roots, let's talk a little bit more about some of the properties of square roots and other roots. Recall that the square root of a number it's the number that you have to take so that that number multiplied by itself gives you 5. So what is the number that when you multiply it by itself, it gives you 5? If I had a 9 in here, of course the answer would be easy, right? 3 times 3 gives you 9. But if I have a 5 there, then it turns out to be an irrational number. So there's the square root of 5. You can get an approximation for it by going to your calculator, and your calculator will give you a pretty good approximation. By the way, another way of writing the square root is writing 5 to the 1/2 power. So this would be 9 to the 1/2 power. Okay, so those are square roots. You also have other roots. You can talk about the cube root of 5. Okay, the cube root of 5 is the number that you need so that when you multiply it by itself 3 times, you get 5. Okay, again, I don't know what that number is. If you ask me what's the cube root of 8, I'd be able to give it to you because 2 times 2 times 2 gives me 8. So I could write that the cube root of 8 is equal to 2. The cube root of 8 is equal to 2. The cube root of 5 is some number less than 2. And again, you can write this as 5 to the 1/3 power, something like that. So that's true for any roots. Roots have certain properties. For example, here's some important properties. The square root of a times b is equal to the root of a times the root of b. Doesn't matter what the root is, it's true for everything, but I'll do it for square roots. So, for example, if I have 36 right here, the square root of 36 is equal to the square root of 4 times 9, right? Because 4 times 9 gives me 36, and that's equal to the square root of 4 times the square root of 9, and the square root of 4 is equal to what? 2, and the square root of 9 is equal to 3, 2 times 3 is equal to 6. And sure enough, the square root of 36 is equal to 6. So when you have a multiplication in there, or division, division works the same way. If you had division here, then this would be division there. Then it works the same way. You can just break it up like that. On the other hand, addition does not work that way. Okay, here's a good example. 9 plus 16. Okay, we know that 9 and 16 is 25. And I know that the square root of 25 is equal to 5. So I know the correct answer to that is 5. If this were equal to the square root of 9 plus the square root of 16, then the square root of 9 is equal to 3. The square root of 16 is equal to 4. 3 plus 4 is 7. See that? So apparently this is not the case, because this is the correct answer, and if you were to break it up like this, you'd get 7. So with addition, you cannot break it up. Similar, remember what we said earlier? If you had 2 plus 3 over 2 plus 1, you can't just cancel out the 2's, but if you had a multiplication there, then you could divide out the 2's. So multiplication usually allows you to do more with it than addition. Addition is a little more persnickety. Okay? So that's all the case. So that's the idea. Let's just do a couple more examples just for practice. If you want to simplify the square root of 18, you could write that as the square root of 9 times 2. And then you could write that as the square root of 9 times the square root of 2. The square root of 9 is equal to 3. 3 times the square root of 2. So that would be a way to simplify that. If I have 1 divided by the square root of 2, that's perfectly fine. That's perfectly fine. But a lot of times in books, the authors don't like a square root in the denominator. So if you want to get rid of a square root in the denominator, you just multiply both the top and the bottom by square root of 2. That's just a fancy form of 1 there. And now you're going to get 1 times square root of 2 on top. And on the bottom, you have square root of 2 times square root of 2. Well, that by definition gives you 2. So that's called rationalizing the denominator. So it allows you to do that. Okay, so that's the end of 6.4. 6.5 is so short, there's really just one problem I'm going to do from 6.5, just to throw in on this same video. Here's the question. Suppose you go to a store and you see a sign that says 30% off, new price is, what do I have? Is $15. Okay, maybe a swimsuit or something like that, or a pair of shorts or whatever, okay? So it's 30% off and the new price is this. And you're wondering, what was the old price? What was the original price? What was original price? And so what you do is you say let X be the original price. We're going to be getting into this in chapter 7 more, but the really cool thing about mathematics is you can use the word let, and you can just start it be let. So if X is the original price, then at 30% off, that means that what your new price is 70% of the original. 70% of the original price is equal to $15, right? Because 30% off, so 70% of the original must be equal to 15. In other words, 7/10 of X is equal to 15. In order to solve it for X, I can multiply by 10 and divide by 7. X is equal to 10 times 15 divided by 7, which is equal to 150 over 7, which is, I'll let you figure it out. It's going to be just slightly let's see, it's going to be 20 something. Let's see, let me grab my calculator. I'm planning to have it. It's going to be 157 divide 21.42. 21.42 was the original price. Okay, so that's a problem having to do with percents, and as I say, we'll get into that a little bit more in chapter 7 as well. Very good. So we'll see you in chapter 7.